Chapter 21, Set A. What page is that on? 379. We are partially into the process of removing the box. And that's where we're headed. We're not going to know what's in the box. So when we take a sample of an unknown population, we just pretend that our sample represents the whole population because we don't really have any other choice. We just pretend that it's accurate, and then depending on our sample size, we can sort of figure out how close we are. Okay? But all of that is going to rely on whether or not our sample was good or representative, because if we have a lot of bias or a lot of other errors that get in the way, then our sample is kind of useless, and in fact can be harmful and misleading. So, set A. Fill in the blanks and explain. In example 1 on page 38, the 317 is the blank value for the number of students in the sample who are living at home. Observed. Okay? There were way more students than that, but in the sample we took, we ended up with 317. Okay? The SD of the box is exactly or estimated from the data. Estimated. So we look at the SD of our sample, and we just say, that's probably pretty close to the SD of the actual box. Okay? See? The SD for the number of students in the sample who are living at home is exactly equal to or estimated as 8. Estimated. So we used the estimated SD to create the SE of 8. So we expect, well, I guess we don't have the percentage, but anyway, we expect to be off by about 8 students. Okay, number 2. In a certain city, there are 100,000 persons age 18 to 24. A simple random sample of 500 such persons is drawn, of whom 194 turn out to be concurrently enrolled in college. How do we know we can trust these numbers? It's a simple random sample. So simple random sample means we obeyed all of the sampling rules. We did everything we could to eliminate bias, selection bias, non-selection bias, right? Every other kind of bias we can think of. So we looked at 500 people. 194 of them are currently enrolled in college. Estimate the percentage of all persons age 18 to 24 in that city who are currently enrolled in college, plus, or put a give or take number on that estimate. So our box is unknown, except for there are about 100,000 people in it. 100,000 people in it. We did it's 100,000 people. We can't talk to all of them. So we pick 500 people, and we pick them correctly. If we didn't pick them correctly, then the whole thing is worthless. When we do this sample, we ended up with 194 out of 500 who were enrolled in college. So apparently this is a college town with a lot of college kids in it. So that, as a percentage, is 0.388. Now we don't have a box. We're just going to pretend that 0.388 is correct. So we build a box that is 0.388 ones, and then 0.612 zeros. Now, is this the real box? No, but if we did our sampling correctly, it's got to be close. Okay. Now what we do is estimate the percentage of all persons in the city who are currently enrolled in college. What's our best guess for the percentage? 38.8. So 38.8 is our expected percentage. We can't get more accurate than that using the information we have. But we would expect that to be off. So we are going to create the SEP, but it's not actually the SEP, it's just an estimated SEP. Well, that's what we do. We just pretend that it's correct. And we're doing the exact same calculations we did in the last chapter, but this time, instead of predicting what our samples will look like, we are using our samples to predict what the box looks like. So in the last chapter, we knew the box, and we said if we were to take a sample, what would we expect to get? And now we're just going backwards. If we have the sample, what do we expect the box to look like? But the calculations and the definitions are exactly the same. These are just estimates. So I have to take the square root of 0.388 times 0.612. So the square root of 0.388 times 0.162. Oops, I did it again. 612. And I get 0.487. Now, just as a review, what does 0.487 tell me? Meaning, that's how far away the tickets in the box are from the average of 0.388. Right? Okay. And then we could take the SD and multiply it by the square root of D divided by D to find the SEP. Or the shortcut is, okay, so this is the SEN, right? But the SEN doesn't do me any good in this case. How come? I want the percentage of the people. So this is the SEN, but when I introduce the divide by D, I get the SE percentage. But there's a shortcut. SD over the square root of D. So the one way to do it is this times the square root of, how many people did I draw? 500. And now that gives me the SEN, which means my 500 people, or sorry, my 194 people could be off up to 10 people, right? Give or take 10 people. But I don't want to represent the sample. I want to represent the whole population. So I take this number and I divide it by 500. And I get 2.1%. So plus or minus 2.1%. So I would expect that 38.8% of the people in this town are currently enrolled in college, but I could be off by 2.1%. Okay? Could I be off by more than 2.1%? Yes, but it's less likely. We're pretty confident that that plus or minus 2.1% will capture the true percentage. How often will I be right? 68% of the time, right? Okay, now let's just do the shortcut. If I did the SD, so I take the SD. What is the shortcut from the SD straight to the SEP? Wow, you guys were all interested in this last week, and now you've forgotten. Uh-huh. Which step are you stuck on? So just close your right eye and look through that left lens. Yeah. Okay. All right. So the first step is writing down the box model. Is that what they put? Writing down the box model? Okay. And then solve it. Number 3. A simple random sample of 100 graduates from a certain college. 48 were earning $50,000 or more. Estimate the percentage of all graduates at that college earning $50,000 or more, plus a give or take estimate. So I don't have the box, but in my pretend box, what am I going to put in there? Is it 48? 0.48 ones and 0.52 zeros. Okay. So my expected value is 48% plus or minus the SEP. I'm not even going to bother calculating the SD because I know what it's going to be. How far away are the numbers from the average? 0.5. How far away are the numbers in the box from the average of the box? About a half. So I'm going to say that the SD is 0.5, and if I calculate it, I said I wasn't going to, but here I go. 0.48 times 0.52, right? Is 0.5. So anytime you have a 1-0 box and you're close to 50%, how far away are the tickets from the box, from the average? Oh, yeah, that won't work. Yeah, don't do that. Okay. So it turns out that 0.5 is the SD of the box, so I need to times it by the square root of 100 divided by 100. So 0.5 times 10 divided by 100 is 5%. Do I need to worry about edges? There are no edges in this box, right? We're not comparing this to a normal curve. So instead of using the box to create the normal curve in a sample, we are using the sample to create the box, and there is no normal curve. We're not even worried about it. So it doesn't matter how many draws we make, but this percentage is high because what? Our sample is really small. Is 100 a good sample? No, that's 5% off. In an election, is 5% a big deal? Most of the time, yes. You want to be within 0.1% or 0.01%. So how can I increase my accuracy? Just make more draws. 100 just simply isn't enough. Okay? And it also depends what's in the box, but in this case, because the average is so close to 50%, then 100 draws is way too small. We'd need more than that. All right, number 4. A simple random sample of 400 was taken for the population of all maturing establishments in a certain state. 11 establishments in the sample had 100 employees or more. Estimate the percentage of manufacturing establishments with 100 employees or more. Attach a standard error to the estimate. Do I even know how many establishments exist? No. In the last problem, we didn't know how many people there were either. So In the problem before that, we knew how many people were in the city, but we just couldn't run out and talk to all of them, so we took a sample. In this case, we don't even know how many there are at all, which is fine. We'll just estimate it, and our sample size will determine our accuracy. So 11 out of 400 gives me we get 2.75%. So I put that in the box. 0.0275 ones, and then 1 minus that will give me 0.9725 zeros. Do I need to find the SD in this case? It's not going to be 0.5 because I have a whole bunch of zeros and a little tiny amount of ones. So is it going to be smaller than 0.5 or bigger than 0.5? So what is the average of the box? 2.75%. Are the numbers in the box close to 2% or not close to 2%? Not close. So our histogram looks like this. Right? These are ones and these are zeros. So these numbers are far away from the average. So I would expect a number probably pretty close to 1. Right? Almost all of the numbers in the box are 1 unit away from 0.2. So we take this 0.0275 and I get, wait a minute, what did I do wrong? Oh, okay, sorry, I just said it wrong. That is close to 0, sorry. So the numbers are close to the average. I said they weren't close. I had it backwards. The average is 2.7%, so 0.027. Most of the tickets in the box are really close to 0.027, right? Let me, okay, I drew that backwards. So here is 0 and here is 1. Okay, right here, that's our average, 0.0275. Are the tickets in the box close to 0.0275? Almost all of them are very, very close. A few of them, 2% of them, are larger. Jayla, does that make sense? Well, hold on. I messed it up. So let me fix my mistake. Okay. Here's our number line. Here is 0. I have a whole bunch of zeros. Okay. And then here is 1. I have a little tiny bit of ones. Right? Where is the average? The average is right here. So what I need to do is find the average distance. Some of them are almost 1 unit away, but most of them are really, really close. So my SD measures the average distance from the average, and almost every one of them is right next to the average. There are a couple of them, 11 out of 400, that are way bigger than the average. That's why my SD is so small, because almost all of the points are right next to the average. Sorry, I messed that up. Okay, so my SD is 0.16, and I want to know 2.75% plus or minus the SEP. So Maddie, how do we calculate the SEP? Okay, do you know how to get the SEN? What do I do with this to get the SEN? Square root of the draws. Is this making sense? Okay. So times this by the square root of 400, which is 20, which tells me my original sample of 11 people is probably off by 3 people. But I don't care how many people I was off. I want to know the percentage because my sample only included 400 of the businesses. I want to represent all of the businesses, so 3 businesses doesn't do anything for me. So I need to turn the SEN into an SEP. How do I do that? Divide it by the number of draws, plus or minus 0.8%. That's less than 1%. Okay? How come I'm so close? Last time I was 5% off. I had a bigger sample, and in this case, the average percentage is so little. That also comes into play. Okay? All right. Is the difference between the percentages in exercise 4 and 5 due to chance error? Didn't I just do? Oh, sorry. Okay. Okay. Sorry. In the same state, a simple random sample of 400 was taken from the population of all persons employed by manufacturing establishments. 187 people in the sample worked for establishments with 100 employees or more. Estimate the percentage of people who worked for establishments with 100 employees or more, and then attach a standard error. So now I have 187 out of 400. Yes, so 0.4675 ones, and I get 0.5325 zeros. What's my SD going to be? It's going to be close to 0.5. It'll probably be just under 0.5. So 0.5325 times 0.4675, and we'll probably get like 0.498 is what I was going to say. Yeah. So my SD is 0.4989. Times that by the square root of 400 over 400. So 0.4, oh wait, let's just do times 20 divided by 400. Oh, divided by 10. And I get 46.7%, give or take 2.5%. Now wait a minute. Why is this one less accurate than the other one? Nope, the samples are the same size. Okay. Do you see what this question, what number 6 is asking? Well, in the first sample, I was taking a sample from a certain city, right? Okay, sorry, got distracted. So, you guys ready to hear this? In number 4, we are looking at a particular state, and we found 11 out of 400. And then, in the same state, for some reason, we ended up with 187, which is a little bit weird, but the original number was 2.7%. That's how many we figured had that many employees or more. Okay? How much wiggle room is there if your average is 2.7%? If you have 2%, can you be off by 5%? No. Why not? Right. Okay. What if I ended up with 98%? Do I have much wiggle room? No, I don't. Because if you have 98%, can you be off by 6%? No, because then you'd be over 100%. Okay? So, if your sample percentage is somewhere in the middle, then your SE percentages will be larger. But if your sample percentages are near the edges, close to 0 or close to 100, then your SE percentages will be smaller. So just saying that increasing sample size will increase your accuracy, that's true, but if your sample percentage is in the middle, it will naturally have larger errors than it will on the edges. Does that make sense? If you're flipping a coin, you are likely to be further away from 50% than if you count up the number of sixes when you roll a dice. Because the percentage of sixes is closer to 0. Does that make sense? So that's what that question is asking. Is it due to chance error? No. It's due to the size of the percentage. Okay. All right. In the next two exercises are designed to illustrate the bootstrap method for estimating the SD of the box. Yeah. So number 7. Suppose there is a box of 100,000 tickets, each marked 0 or 1. Suppose that in fact 20% of the tickets in the box are 1s. Calculate the standard error for the percentage of 1s in 400 draws from the box. So once again, we have a box, and we even know what's in it. So 0.2 1s and 0.8 zeros. So how do we find the SD? The square root of 0.2 times 0.8. So the square root of 0.2 times 0.8. 0.4. What does that mean? The numbers in the box, on average, are 0.4 units away from the average of 0.2. Okay. So now we need to calculate the standard error for the percentage. How will we find the standard error? 0.4 times what? Square root of 400 over 400. Or the faster way to do it is 0.4 divided by square root of 400. So 0.4 divided by 20 gives you 2%. Okay. 3 different people taking simple random samples of 400 from the box in exercise 7 without knowing its content. The number of ones in the first sample is 72. In the second, it's 84, and in the third, it is 98. Each person estimates the SE by the bootstrap method. So we're going to throw away the box. We don't know what's in there. But the first person got 72 out of 400. So their estimate is going to be 0.18. The next person got 84 out of 400. Is 0.21, and the last one is 0.24. So each person independently is going to calculate their standard error. So this one will be the square root of 0.18 times 0.82, right? And then we're going to divide that by, well, let me write it out. 400 divided by 400. Right? What do you get for that? Well, we want the SEP. 1.9. Okay. And this one you end up with 2. And this one you end up with 2.1. So let's look at how we did. So the first person says 18% plus or minus 1.9%. Did that capture the true value? What is the true value? 20%, right? We know there are 20% ones in the box. Okay, so this person did a sample of 400 people, or 400 whatever, and then ended up with, they thought that the box contains 18% ones, give or take 1.9. They were really close. They were off by 0.1, and actually it's probably less than that, because it was 1.9 something, I'm assuming. So they just about got it. They were really close. Okay, the next person says 21%, give or take 2%. Did they capture the true value? Yes. The next person says 24%, give or take 2.1%. Did they capture the true value? No. And sometimes that happens, right? Which is why if you only take one sample, right, you have to be kind of wary because that sample could be wrong. All right. Number 9. In a certain town, there are 25,000 people aged 18 and over. To estimate the percentage of them who watched a certain TV show, a statistician chooses a simple random sample of 1,000. As it turns out, 308 of the sample people did see the show. Complete the following table. The first 3 lines refer to the sample percentage who saw the show. Okay. So we don't know what's in the box. What are we going to put in the box? So, we do know, sorry. So it says, as it turns out, 308 people of the sample did see the show. So complete the following table. The first 3 lines refer to the sample percentage. So we have our observed value is 30.8. What does that mean? That's how many people we found when we did our sample. Okay, our expected value is 30.8%. How come? We don't know what's in there. So we are going to pretend that our observed value is real. Could it be wrong? Yeah, we just learned in the last one. It's possible that we're off by so much that we don't even capture it with our standard error percentage. But that's okay. It's the best we can do. So the SE do we know what the known SE actually is? No. But we can estimate an SE. Right? So the known can't happen, but if we take the square root of 0.308 and we multiply it by 0.692, that will tell me the SE, or the SD. Sorry, this is the SD, and then we can use that number, multiply it by the square root of 1,000 divided by 1,000, and that will tell us the SE. But is it the actual SE or is it the estimated SE? Estimated. And then the number of draws known to be 1,000. Okay? All right.